Okay. Just one question that happened during the break that I thought was worth addressing, this issue of LDA and when to use it and when not to. LDA is perfectly fine in this synthesis here. An organic chemist probably wouldn't bother because you can get away with an acid that's much weaker and cheaper. If the pKa of that proton is around 11, then that means you could quantitatively remove that proton with sodium ethoxide, and so you probably would. Nevertheless, it's not wrong to use it, and so that's fine. The place where you wouldn't want to use it is here, where you're proposing to remove an alpha proton whose pKa is like 20 or 30 in the presence of a much more acidic proton whose pKa is like 4. Not just LDA, but even sodium ethoxide would not do the job here. You're simply going to deprotonate the acid. So, okay. We had another one we wanted to do, and that was this carboxylic acid. I've drawn it in a little bit of a funny way so that you may not recognize what bonds you need to make. So take some time, stare at it, propose a synthesis. Try to do this in about 5 minutes or so, and use either of those two starting materials, the beta diester or the acetoacetic ester. Only one of them works. You got to figure out which one it is. All right, so go for it. Sorry, show what? Yeah, I'll copy those two allowed starting materials. Copy, paste, shrink. While you're doing that, I'm answering my son's history questions. Yeah. Where to learn how to do that actually? Chapter 18 or maybe, yeah, you buy them. That's right. Just put money as the. You got to start with those two, but any other sources of carbon are fine. Yeah. I need some help. What are popular products from the 2010s? I presume 2010s. iPhones. Crocs. Low-waisted shoes. Okay. Ah, yes, the fidget spinners. Did Rubik's Cubes make a comeback during that time? I had a kid that was into that. All right, if you want to talk to your neighbor, compare your syntheses, see if you can find any mistakes or anticipate any issues. Silly bands, I don't even remember those. What's that? Oh, those, yeah.
They have like 500.
Yep, okay, I remember that. Okay, what do we got for this synthesis? You want to start with this diester, okay. Why to choose? Yeah, let's talk about that. Why do we choose the diester instead of the beta keto ester? Yeah, look at what is still, so find the alpha carbon and look at what's on the alpha carbon. Is it a ketone? If so, you want to use that. If it's an acid, you want to use that. Okay, so what are the alkyl groups I'm going to install? Yeah, I got two of them, right? Does it matter in which order they go on? No, they're both primary carbons. So yeah, you're going to do the standard 1-2 punch with sodium ethoxide and then either one of these alkyl halides. It's fine to do the other. I don't think the order matters here. And then lastly, that would get you to the intermediate product, that's the diester. Then you use hydrolyze the ester and heat to decarboxylate, and that should get you to your alpha-alpha dialkylated acid. Okay, good. So if you want more practice on this and you can't find it in the practice exam, go to the end of the chapter. There's problems called under the heading synthesis, and practice there. There's also some problems under the heading challenge problems that sometimes push you a little bit beyond what we're talking about in class, but we'll give you some practice on these kinds of things. Mostly, it's trying to open up your eyes so that when you see this product, an alpha-alpha disubstituted ketone, in your mind's eye, you're thinking backwards to, oh, I could have started with this beta keto ester. Yeah?
As an intermediate with the heat, would you have two alcohols at one point?
As an intermediate along the way, yes, you would have gotten the enol before tautomerization. Yeah. Something like that. Yep. Okay. So I want to show you an example. Decarboxylation happens all the time in nature. There's a lot more we could say about it. And in fact, when nature wants to use an enolate, often it will mask that enolate with something that can decarboxylate. But I think we're going to wait on that. But I do want to show you an example of decarboxylation in biology. And this is going to be the biosynthesis of histamine. Histamine is a molecule that is derived from an amino acid, and it's involved in the allergic response. I don't know more biology really than that. Here is the structure of histamine. Whoa. And you can get it. I don't want you to memorize what the structure of histamine is, by the way, so just don't worry about that. It is a product of a precursor amino acid. That is called histidine. I'm just. That's right. Can't help you if you're going to make words up. All right, and notice what's missing. You've lost CO2. Now, remember, when we did decarboxylation previously, the reason this can happen is because you have, let's see, where was it? Right here. Beta to the carboxylic acid, you have a ketone that acts as an electron sink for the electrons in this bond between the carbonyl carbon and the alpha carbon. If that ketone isn't there, you don't remove the proton from the carboxylic acid, you don't form the pi bond of CO2, you don't leave electrons behind from CO2 to form the enol. So you can tell that looking here at the structure of histidine, here is the alpha carbon. There's no ketone on the alpha carbon. There's no ketone, or rather there's no ketone at the beta position. No ketone, no decarboxylation. So nevertheless, the decarboxylation happens, which tells you that there's got to be something for the enzyme to do. All right, so we're going to use an enzyme and a cofactor. The enzyme is called a decarboxylase because it catalyzes decarboxylation reactions. Kind of a boring name. There's a cofactor, and the cofactor is called PLP, which stands for pyridoxal phosphate. And I skipped discussing pyridoxal phosphate in a previous lecture when we were talking about formation of imines. but we're going to talk about it now. If you followed along with the study guide and read the associated portions of the text, you will have already seen this cofactor. I don't want you to memorize its structure, but I do want you to observe, as we talk about what this cofactor does, how it satisfies the requirement for putting a ketone type group at the beta position. Pyridoxal phosphate, PLP, is an aldehyde, and histidine has an amino group. So we're going to combine pyridoxal phosphate and PLP and histidine, and we're going to do imine formation. And I'm going to refer you to your notes and to the text for the mechanism of imine formation. That's not what we're talking about today, but you should have mastered that already. I'm going to draw the imine product that you get from this reaction. Dun, dun, dun. I guess that's good enough. Maybe we'll. I could have drawn all the rest of PLP, and maybe should. Don't really want to. One of the skills that I've been telling some of you about in office hours is how to recognize when you can just abbreviate stuff and make your life a little bit easier. So it would have been fine for me to just show an R group there. But we'll go ahead and draw it. But you can, for now, sort of ignore all of the rest of this.
I have a quick question. Is this PLP or is that some, or the previous one that you drew, is that PLP or is it something else?
This is PLP, yes, pyridoxal phosphate.
What's
The next one, this over here, I don't know what that's called. Yeah, that's the imine. The imine linkage between the carbon of PLP and the nitrogen of histamine. It's an imine bond. So yeah, you react the amine with the aldehyde to get an imine. Yep. All right, now, let me copy, sorry. Let me copy this beta keto acid. And I want you to relax your eyes just a little bit. And do you see any structural similarities between the beta keto acid and the imine that I just formed? With the beta keto acid, you've got a carbon-oxygen pi bond on that beta carbon. Now here it's sort of switched, right? Instead of a carbon, you got a nitrogen, and then instead of an oxygen, you got a carbon. But you do have a pi bond between the atom at the beta position and the next one. In other words, this is, if you relax your eyes a little bit, it starts to look like a beta carbonyl type compound, right? Or in other words, imagine what would happen over here if the beta, so with the beta keto acid, one of the things I didn't, well, even from this perspective, I showed you decarboxylation under acidic conditions. It can happen under basic conditions as well. But the point is that once CO2 leaves, there's a place for the electrons that are left behind to be stabilized by resonance. That's not what we saw previously under acidic conditions, but the principle's the same. The CO2 can't leave unless there's a place for the electrons in this bond between carbonyl carbon and alpha carbon to go. The question we should ask is, here, if CO2 leaves, is there a place for those electrons to go? Would they be resonance stabilized? So let's actually just do that reaction. At physiological pH, it turns out that that proton isn't there. So we'll bait and switch you and rearrange some things, but actually that proton was never there to begin with because its pKa is like 2 and we're at pH 7. You okay with that proton being gone? It was never there in the first place. All right. So now let's ask the question, if these electrons kick down and we leave the proton, we leave those electrons behind on the alpha carbon, is the resulting conjugate base resonance stabilized? So here's the CO2 that left. Yikes. Oh, yes, I am. Thank you. All right, we lost CO2. Now let's look at, and the electrons that were in the bond between the carbonyl carbon and the alpha carbon are now just sitting on the alpha carbon. Is that negative charge resonance stabilized? Test question. Which carbons in that molecule share the negative charge by resonance? Do you see why we talk about this? This one. Do the resonance two-step, move these here to form a new pi bond between alpha and nitrogen. If we stop there, we'd have too many bonds to nitrogen, so we would have to break the carbon-carbon bond, carbon-nitrogen pi bond and move the electrons in the pi bond onto the carbonyl carbon, which means the negative charge could be there. Still with me? You got that? Where else? And there, and there, and there. Okay? That's why the decarboxylation can happen. You stick PLP on your amine to make the imine, and suddenly you have this vast electron sink that's ready to accommodate the negative charge that's left behind when decarboxylation happens. This is the base catalyzed version, really, of the decarboxylation that I showed you here. But the point is that when that decarboxylation happened, there was some place for the electrons from the carbonyl to alpha carbon bond, some place for them to go. The electron sink there was this ketone. Here it's this rather large imine group from PLP, right? At that point, the chemistry's done. We simply pick up a proton from some acid, probably an acidic group provided by the enzyme. At that stage, all that's left is to do imine hydrolysis, which I'm not going to show you because, again, you've done that reaction before. And if imine hydrolysis is a struggle or you don't remember it, that's worth going back through. Hydrolyze the imine. Using water and some acid catalyst. The enzyme's going to do that. In doing that, you're going to break the bond between the carbonyl carbon and the nitrogen, and you're going to liberate your histamine. Histidine is an amino acid that's found in proteins. Histamine is a signaling hormone molecule that helps with the allergic response. Dramatic change, presence of the CO2 group. And it's all involves this key decarboxylation step, which, again, if you relax your eyes a little bit, this is decarboxylation of a beta carbonyl type acid. All right. Any questions you want to ask about that? Yeah.
So in order to do this entire sequence that we did, we had to add PLP to.
That's right. We had to add PLP to install the beta carbonyl type group. So there was a place for the electrons to go. Yep. All right. That's PLP. When we get to metabolism, we're going to see a couple of examples, especially in the citric acid cycle, where we're going to try to get to something that's a beta keto acid so that we can do a decarboxylation. Some of the CO2 you're breathing out comes from decarboxylation reactions. All right. The last thing we need to talk about in this chapter is sort of your text starts with this, but it's kind of just, it's a maybe cute little example of doing reactions with the alpha carbon. And it's certainly not as cool as the stuff we've talked about. So we're ending with, I guess, the boring stuff. How's that for an exciting introduction? Are you glad to be here today? This reaction is called alpha halogenation of carbonyl compounds. And this is useful because you're going to install a leaving group at the alpha carbon where you can then do subsequent reactions. So here's the classic example. You can do this under acid or base catalyzed conditions. We're going to focus just on the acid catalyzed conditions. There's some complications with the base catalyzed conditions that are interesting enough, but we're not going to worry about them. So you do this reaction with bromine and in the presence of acetic acid. And this is both your acid catalyst and your solvent. And the product puts a bromo group on the alpha carbon. That's why it's called alpha halogenation. All right. So mechanistically, what's going on here? Under acidic conditions, you have an equilibrium between the two tautomer forms of this ketone. You have the enol and the keto form. And if you want, we can draw that mechanism. Under acidic conditions, it's pretty easy. All you have to do is protonate the oxygen to get to an oxonium ion. And then you remove the alpha proton using the conjugate base of your acid. This is tautomerization. We're only changing the location of a proton and a pi bond. Sorry. There are, whoops, I meant to use the eraser there. So there's the tautomerization process. Once you have the enol form, you're going to do a reaction that's going to look maybe a little bit similar to halogenation of an alkene, only pi electrons from the alkene or from the carbon-carbon bond, pi bond, are going to attack the bromine. With alkene halogenation, we would have had electrons from the bromine go down and attack the other carbon. We don't need that here because we can have electrons from the oxygen kick down to form a new pi bond, and that gives you your product. You can draw this reaction multiple ways. If you prefer this structure of the enol, in which the alpha carbon has a negative charge on it, then it's maybe much more straightforward just to have that negative charge attack the carbonyl carbon. I guess I should say, whoops, that we're not quite there. After we've made the carbon-bromine bond, you still have this protonated oxonium ion, and we'll regenerate our acid using the conjugate base of the acid to remove the proton from the oxonium ion, and that gets us to the product. So that's alpha halogenation. As I said, you can do this under basic conditions. The challenge is that basic conditions tend to add more than one halogen group at the alpha carbon. So we're just going to ignore that and use the acid catalyzed conditions. So your product here, if we're thinking about structural patterns, is an alpha halo ketone. You can do this with chlorine as well. All right, anything you want to ask about that? Yeah. You know, that's a great question. Could the reaction add another bromine on the other side? Sounds reasonable to me. Once you put the bromine here, though, this proton, because of the electron withdrawing nature of bromine by electronegativity, tends to be more acidic than that one. It seems reasonable, but so I don't really have a great explanation for why not. Yeah. So I feel like the mechanism here isn't necessarily one that you would need to memorize. If you understand carbonyl chemistry, I feel like you can figure it out. The detail, though, as to only adding one bromo to the alpha carbon, that's probably, memorization is probably the right tool for that. Now let's just talk briefly about what you can do with alpha halocarbonyls, because this opens up a wide variety of synthesis for you. So let's just suppose you have, just because we like to inspire terror, we've got this 6-membered ring. And let's do the alpha halogenation reaction. And then let's think of all the things we might do with that alpha halocarbonyl compound. So one option is, let's just add a nucleophile and do an SN2 reaction. You know, so maybe we'll be general. But if you see something that could have been a nucleophile, alpha to a carbonyl group, you should be thinking, I could have made that via the alpha halo carbonyl compound. As an example, let's use some thiolate, a negatively charged conjugate base of a thiol. Here is the new bond we made because we had that leaving group present. Oops, sulfur, there we go. So that's one example of a synthesis reaction we might have done. If you have the bromo group at the alpha carbon, you might have also done an E2 reaction to give yourself this product, which happens to be an alpha beta unsaturated carbonyl compound. We've seen those before. We use them as starting materials for a particular kind of reagent. Cuprates, right? An example of a reagent that would do this E2 reaction would be tert butoxide. Another example that your text uses, and I don't know why your text uses this other than presumably it works, is to use the base lithium carbonate. Carbonate is CO3 2-. It's a stronger base than its conjugate acid bicarbonate, which we use in baking. So you can think of it just as lithium with 2 counterions of lithium with the carbonate conjugate base. Also, as an additive, you add a lithium bromide. I'm not sure why I'm writing this down other than you're going to see your text use lithium carbonate and lithium bromide as a way for converting the alpha bromoketone into the alpha beta unsaturated carbonyl compound. I don't know why your text is choosing this other than Professor Smith, who wrote the text, is a synthetic organic chemist. She likely looked it up in the literature, found this example, saw that it worked in a lot of cases, and gave it to you as an example. So you may have to just sort of memorize that this is just a base that's going to participate in an E2 reaction. I present it here to you not because I want you to memorize it, but just because you will encounter it in some problems in the text. And I just want you to know what to do with it when you see it. Having made that alpha beta unsaturated carbonyl compound, you guys are right. What could we do? Well, let's see. If we used some kind of cuprate reagent, we could do conjugate addition. That's addition to the beta carbon. That would give us this product. If we used, in contrast, an organolithium reagent or a Grignard reagent, we could do regular nucleophilic addition to the carbonyl group. I suppose we could also use lithium aluminum hydride or sodium borohydride to reduce the ketone to the alcohol. And then there's a whole bunch of other things we've learned to do with ketones, right? So any of those would be accessible as well. We could form acetals, we could form imines. The point is you have a lot of options that are available to you once you've installed the alpha halo compound. All right, questions? You're pretty ready to be done. I'm pretty ready to be done. Let's call it good. We'll see you next time. All right, so we have been talking about enolate alkylation. Today is our second of 2 days on chapter 17. If you weren't here on Friday because you were worried about the test, the lecture should now be posted on Learning Suite and you need to catch up. So recall that we had identified sort of a workaround method that allows us to take advantage of making the enolate that is fastest to form and also the most stable enolate. And this is by using one of these so-called beta dicarbonyl compounds, where the protons that are alpha to two different carbonyl groups are the most acidic ones, and they get removed fastest, and the enolate they form is the most stable of the options. For example, notice with this acetoacetic ester, we said the pKa of the protons that are alpha to two carbonyl groups here, one a ketone, the other an ester, that pKa is 11 versus the pKa of a proton that's alpha to just one ketone, and that pKa is 20. So it is the most stable enolate to remove these protons that are alpha to two carbonyl groups, but that's also 100% yield quantitative, no question at all. All right, and the second issue we're solving is that we are able, using an inexpensive base, remember its conjugate acid is ethanol, pKa 16, we can remove this proton 100%, very fast, irreversible. We get this enolate, which is both the kinetic and the thermodynamic enolate. And then we can use that as a nucleophile in a subsequent SN2 reaction. And the beautiful thing is that your electrophile, the alkyl halide, never has to see sodium ethoxide, because you've 100% consumed the sodium ethoxide by the deprotonation reaction. So that avoids the problem we were talking about last time with incomplete enolate formation, where we were worried that some of the remaining sodium ethoxide was going to do Williamson ether synthesis. All right. Any follow-up questions on sort of what's going on here? Yes?
How does that sodium OET perform differently than LDA?
It does exactly what LDA would do. The only thing is that this is weaker as a base than LDA, but we're just using an enolate there. We're just using a ketone compound with especially acidic protons. Yeah, so in this case, sodium ethoxide is a good enough base to completely 100% remove the alpha proton to give you the enolate. Whoops. Okay, others? All right. Now, we mentioned that this is a good method for alpha alkylation of enolates. So starting material is here, product is here, one alkyl group. We also said that this gives you an interesting opportunity to put two different alpha alkyl groups on your enolate, because after you put one on, you still have a proton that is alpha to two carbonyl groups and should still be acidic, should still have a pKa of around 11. So you can take one more equivalent of base, remove that proton, and then do a subsequent alkylation reaction. So if you want to generate alpha-alpha dialkylated molecules in a really efficient way, this is one of the strategies. I showed this strategy to you for this beta keto ester. That is, you have a ketone on the beta carbon. But it also works for the beta diester over here. So what I showed you for one works for the other. Other questions? Yeah.
Why would the sodium ethoxide not remove the second hydrogen initially? Like, how could you?
Why do you just remove one and not two?
Yeah.
Okay. I don't know if you remember learning about polyprotic acids in Gen Chem, but for example, for phosphoric acid, I forget, but I think the first pKa is 2 to generate H2P PO4, and then the second pKa is around 7 HPO4 minus. And I forget what the third pKa is. But in general, this is a general phenomenon for acids that can lose more than one proton. The first one is the easiest to go. And if you think about it, the reason is that if you removed a proton, if this proton from the monoanion, it would be a dianion. So you have some electron repulsion. Yeah. So I don't actually know what the pKa is for the proton where it's already negatively charged. Presumably it's high enough that sodium methoxide doesn't remove it. Okay, good. What else? Yeah.
Sorry, so up on here you have these two different groups, with one with OET on both sides and one with just the first side. Why is the one with both like a higher pKa?
Why is it a higher pKa? Remember, good question. Remember that the thing that makes alpha protons acidic is the fact that they can be resonance stabilized in the conjugate base. And that resonance structure involves donating these electrons into a pi bond between the alpha carbon and the carbonyl carbon. So the more electron poor your carbonyl carbon is, the better that resonance structure should be. In the ester, as opposed to the ketone, you have lone pair electrons on the oxygen that are actually donating electron density by resonance into the carbonyl carbon to begin with. So ester carbonyl groups are less electron poor, they are more electron rich, and therefore when you remove the alpha proton, it's not as good of a deal to stabilize the anion by resonance because you're already doing a lot of resonance donation into the carbonyl carbon. All right, good. What else? All right, we're not done. There's actually more you can do with these products. But before moving on, you have this alpha-alpha dialkylated product. I'm going to show you another alpha-alpha dialkylated product, and you're going to hate it because we're actually going to do the two successive SN2 reactions, and we're going to make a ring of some size. And if you are like students that I have had in the past, when you see a ring of some size being formed, your brain wants to go all SpongeBob on fire. And so let's work through this and see if we can think through it systematically, and I'll try to give you some tools for doing this. Okay, first, remember your proton alpha to 2 carbonyl groups is acidic enough that sodium methoxide can 100% remove the proton. So your first step is to make the enolate. Boring so far. Next, we're going to introduce 1, 2, 3, 4, 5. Sure. This bis halide or dialkyl halide. We've got a halide on either end, so it's a double electrophile, and that's a negative charge. So first we do the SN2 reaction. So far, it's just exactly what we did above. We make a new bond, which I'm going to show in red. Sometimes it's helpful to number the carbons so that you don't get mixed up. So this is carbon 1. 1, 2, 3, 4, 5 carbons, and then a halide. 1, 2, 3, 4, and 5. Okay? Good so far? Sufficiently boring. All right, we still have a proton that's alpha to 2 carbonyl groups, and that proton is still acidic with a pKa of 11. Because that proton is still acidic, we can do something that would otherwise be somewhat risky. And that is, we're going to add another equivalent of sodium ethoxide. Now, if that very acidic proton were not there, I would be worried that ethoxide was simply going to come in and attack the alkyl halide to do SN2 chemistry to make an ether. But it turns out that the deprotonation reaction, because proton is small, removing that proton is faster than attacking the carbon. And so we don't have to worry about ethoxide attacking this alkyl halide in an SN2 format, because we're able to completely and 100% distract the ethoxide from that option with a much easier acid-base type reaction where we remove that alpha proton. All right. So 1, 2, 3, 4, 5. Yeah, we are, aren't we? Missing a carbon. And that is why we count them. Okay. Now you have an enolate, and in the same molecule you have an electrophile. Intramolecular reactions are generally fast. Do you remember how when we learned about the SN2 reaction, the rate of the reaction was equal to some rate constant times your nucleophile times the concentration of your alkyl halide, which reflected the fact that for the reaction to happen, 2 different molecules had to find each other in solution. And the only way to make that faster would have been to increase the concentration of the two reactive partners to the point where they could find each other. When the nucleophile and the electrophile are in the same molecule, you don't have to worry about that anymore. They don't have to find each other. They're already tethered together. And so it's actually very quick for the internal SN2 reaction to happen. Now, some of you are bothered by the fact that your negative charge nucleophile is connected to your alkyl halide. Some of you are looking at that and saying, what is going on? I've got no idea. Ignore that for the moment and just focus in on the new bond that we made. Okay, so at this point, the first bond that we made, we said we were using red. We'll call that R. The second bond that we made, maybe we'll use a different color arrow. I hate to do this, but we'll use blue. We'll call that R prime. Not so hard, right? Now let's connect the two. The first atom that's bonded via that red bond is 1. The atom that's bonded via the blue bond is 5, and they are connected by atoms 2, 3, and 4. So I'm going to temporarily erase my R group. This is 1. This is 5. 2, no? 3, 4. And actually we can clean that up and make it look prettier. One, 5, 2, 3, 4. Ta-da! We just made a 6-membered ring. And notice that of that 6-membered ring, 5 of the atoms come from our alkyl halide, and 1 of the atoms is our alpha carbon. Okay? All right, so naturally, because organic chemists like making rings, you can pretty well guarantee, I can pretty well guarantee you're going to see something like this in the future. And you're going to have to get the ring size correct. So that's probably worth a little bit of practice until you've got it. Anything you want to ask about that? Yes?
So that's just gonna automatically happen as soon as you add that second dosage of sodium.
That's right. Second dose of sodium methoxide, boom, intramolecular SN2. Yep. Can you make smaller rings? Yeah, you simply tailor the size of your linker between the 2 halides for whatever ring size you want. So the question, I think, is if I go smaller, I'm going to get more strained rings. At what point does that become not doable? I think, I'm trying to remember, I think your text may even provide examples of a 3-membered ring forming. 3-membered rings are ring strained, but they actually are all over the place in OChem. So, you know, I would say this is a decent way for making rings in the 3 to 7 range. There's actually an area of chemistry called physical organic chemistry, and you can take my class 552 in fall of 2023, where we will talk about what rings are favorable and which rings are not. Very few people have ever taken me up on that offer. I need to work, it may not be the sales pitch, it may be the product actually, you know? Yeah.
Does this reaction still work with the ethers on both sides?
Does it still work with what?
Like when the ethers are on both sides?
Yes. Will this work if you have the diester? Yeah. Yeah, we have just chosen this as an example, but everything we say for this acetoacetic ester, whoa, up in there, is also going to be true for this one. Yep. Okay, yeah.
If you have other groups on what you attach to, will it automatically go to the most stable conformation, like the Sp2023 conformation?
What? I'm sorry. If you have other groups attached to what?
So if you had other groups attached to the tail that you put on it originally, once it kind of snaps together, will it arrange itself to be in the most stable?
Oh,
shared
so
conformation?
are you thinking about harder test questions? You're wondering if I have stuff there, what the most favorable chair is? I don't think, I mean, I could ask a question about that, but I've never done that in the past. Maybe that's, I'm sorry. I'm threatening your life at this point, actually, or causing others to threaten your life. No, yes, presumably there would be some most favorable conformation. I don't know how to ask it in a question necessarily about that, so yeah. I mean, at worst, that would involve making sure that you got stereochemistry in whatever substituents were here to stay the same when you got there, I think. But yeah. Okay. What else? Not done with the beta diketo or the beta dicarbonyl compounds because there's a reaction I can do. Notice that I start with a beta dicarbonyl compound. Oops, I'm erasing stuff. I alkylate it either once or twice, but my product is still a beta dicarbonyl compound. And with any of these products, the monoalkylated, the alpha-alpha dialkylated, or the alpha-alpha dialkylated cyclic compound, I can do a subsequent reaction, which you're not going to like, but which nevertheless is useful and allows us to introduce a new concept. So you can follow everything that we've just talked about with a two-step, well, it's a single step, but two things happening in it. ester hydrolysis and decarboxylation. All right, so let's just take the product we barely formed, the cyclic product, and we won't, I mean, maybe we will do the mechanism. That might be decent review from chapter 16. Let's add H3O plus and water. This would be acid catalyzed ester hydrolysis. So, would you predict, is water a good enough nucleophile to attack the ester directly? No, because you'd take a neutral nucleophile and generate a negatively charged tetrahedral intermediate. So probably you gotta protonate that ester oxygen first to generate the oxonium ion. It's then at that stage that the oxonium ion is electrophilic enough for water to attack. Whoops, missed. That's going to generate the tetrahedral intermediate at what used to be the ester oxygen. At this stage, it would be simple for that neutral oxygen to have its electrons kick back down and remove the oxygen, remove the sort of water nucleophile. That would simply be the previous step. But we're doing this reaction in an excess of water, and that's going to tend to try to drive the reaction forwards. So instead of kicking off water, we can actually use the conjugate base of our acid to trade protons around this tetrahedral intermediate to change who is the good leaving group. Now we're going to protonate, the basically alcohol oxygen to convert it to a good leaving group. It's now a good enough leaving group for a neutral oxygen to kick off. All right. So now we've got, and then we'll have water remove the proton, and that will give us the following product. Which is a beta keto acid. So all of that was just a review of ester hydrolysis mechanism. We're just hydrolyzing the ester, all right? Anything we need to review there? Anything you're uncomfortable with? So that was the boring part. Beta keto acids are special because they can undergo an interesting reaction where they lose CO2. And this usually happens spontaneously if you add heat. So at this stage, if we add heat, the O chemist's fiery triangle of doom, we can convert that beta keto acid, run out of space. And this is irreversible. We can convert the beta keto acid into the following ketone and CO2. If you count the atoms, we haven't lost any atoms. The CO2 is here. This proton ends up here. All right, and that reaction is called decarboxylation. And the insidious thing about decarboxylation is that I can now show you this product, this alpha-alpha disubstituted ketone. And you have to, by experience, realize you could have made that from the beta keto ester starting material way back here. And we choose this because it's a very, very easy way to do the bis alkylation reaction, and then the decarboxylation conveniently gets rid of the CO2 group. So this whole reaction series is an insidious one when it comes to testing you on synthesis, because most of you without a lot of experience are not going to look at this product and say, oh, I know what the starting material was. It's this completely different thing up here. So you have to test, you have to work on that until you can see that and get it. I want to show you the mechanism of decarboxylation, and we'll talk about the mechanism because it's useful in biology. So to start with, the decarboxylation mechanism, I'm going to draw the beta keto acid in a slightly different way. I'm going to put the OH group of the carbonyl here. And I want you to see that, let's try to make that clearer. On that, here's carbonyl carbon, alpha carbon, beta carbon. Lone pair on the beta keto group is engaging in a hydrogen bond with the proton on the carboxylic acid. And in fact, that hydrogen bonded interaction involves 6 atoms. It's a 6-membered ring. And one thing you need to know about 6-membered rings in OChem is that atoms that are atoms that are part of a 6-membered ring interaction can get close to each other. We could draw a chair. We won't, because that would be too painful, but we can draw a chair in which the proton that is bonded to this oxygen is also close to the carbonyl oxygen. All right? So it's not such a huge step if that lone pair on the carbonyl oxygen of the beta keto group is already hydrogen bonding with the acid proton. It's not such a big step to imagine completely removing that proton. And then it's not such a big step to imagine these electrons in the oxygen-hydrogen bond coming down to form a new pi bond. And then these electrons in the bond between carbonyl carbon and alpha carbon coming over here to form a new pi bond. And these electrons moving up onto the carbonyl oxygen to give you the following intermediate and CO2. So there's a lot of things going on at once. Basically, this hydrogen bonded ring that we formed fragments in a way that moves the proton from oxygen 5 onto oxygen 1. And then the sigma bond between 5 and 6 becomes a pi bond between 5 and 4. The sigma bond between 3 and 4 becomes a pi bond between 2 and 3, and the pi bond between 1 and 2 breaks and becomes a lone pair on the oxygen. Okay, that's the decarboxylation reaction. And this can happen not only for the molecule I've shown you, but anytime you have a beta keto acid or a beta carbonyl type acid. It's a general pattern. Now, take a look at this product that we just formed and compare it to the product over here that I told you was the product. What's the relationship between those two? Tautomers, good. Right? They differ in the location of a proton and a pi bond. You can interchange tautomers simply by proton transfer. This is the product of that decarboxylation is an enol. The product over here that I showed you is a ketone. They are tautomers, so we can interchange the two simply by tautomerization. So we're going to do that. And there's maybe a couple different ways you can push arrows. I'll show you the one that makes the most sense to me. The enol has a resonance structure that looks like this. And so remember, we're still under acidic conditions. We can't use OH minus. We're going to use H3O plus to protonate the alpha carbon. And then we will regenerate our acid by using water to remove the proton from the oxonium ion. And that's going to get us to the ketone product. How are we doing on lighting? Do I need to mess with that so that you can see better?
That's good.
Okay. All right. Decarboxylation. Dallin wants me to answer like 10 questions for an interview for history. Do you? Shall we answer them together?
What history of this boat was it like?
What was it like when George Washington was president? Well, let me tell you. Okay, questions about decarboxylation? Yeah.
So that initial reaction where it makes the enol
Yeah.
is the driving force for that? Is it mixed with an acid or anything, or is that just resonance?
Oh, this here? These two?
No, the reaction before that, making the enol.
The driving force for that is loss of CO2, which is a gas, and that's a big increase in entropy.
Okay.
Yeah.
And does it react with anything for that to be initiated?
You just need to cook it. You need to, the heat is all you need for that. That's what's represented by here. I'll put that heat arrow here as well. The heat is all about overcoming the kinetic barrier, giving yourself the activation energy to make the reaction happen. Okay. Yeah.
So earlier when we used the monoester compound, that was because we knew that we could take it out with decarboxylation at the very end.
Yeah. So before, when we started with acetoacetic ester, you don't have to decarboxylate. You can just avoid hydrolyzing the ester, and you can stop at the mono or dialkylated product. But if you want to get rid of the ester, you can by hydrolysis. Yeah.
Does it work for the diester?
Does it work for the diester? You bet.
You just have to process.
So let's, for the diester, let's go ahead and make, I don't know, let's just save ourselves time and make just a monoalkylated product. Oh, this will be fun. Let's put a benzene ring in there, shall we? All right, why not? So here is the monoalkylated product. Here is the new bond that we made. 1, 2, and then benzene ring. Carbon 1, carbon 2. Okay, so what happens at this stage if we do H3O plus and water? We're going to hydrolyze both esters, right? So that's going to have us, get the product that looks like this beta diacid. I'm going to use pH for phenyl group. Beta diacids are also subject to decarboxylation because we can redraw that beta diacid like this. Same situation. Lone pairs on the carbonyl are already hydrogen bound to the acid proton. You'll get initially this enol tautomer of your carboxylic acid, and you lose CO2, and then that enol will tautomerize via the approach I just showed you above to give you your alpha alkylated acid product. So yes, you can do this with the diester as well. And your product is an alpha alkylated carboxylic acid. Now, if you're shown this as a product, you should make that product. Already you should be worried about making that product via conventional enolate alkylation. Some of you are going to propose, oh sure, I'll just start with the carboxylic acid, and then I'm going to use LDA and then my alkyl halide, and boom, that ought to give me the product, right? Wrong. Why doesn't that work? LDA is a strong base. You're going to deprotonate the acid. You just wasted a lot of reagent, probably started a fire. Okay? So, if you see an acid that you have alkylated at the alpha carbon, a great way to do that is to start with the beta diester you are able to do all the acid base and SN2 chemistry to make your bond between the alpha carbon and your electrophile before the acid's even present. Then you hydrolyze the ester. Then you get rid of one of the two carboxylate groups through the fiery decarboxylation. It's not actually fiery, it's really boring, it bubbles. And that generates your product. Yeah?
Theoretically, could you use a protecting group to take off the H?
Yeah, could you use a protecting group strategy to get rid of this proton? Frankly, making the ester is a protecting group strategy. Yeah, we didn't talk about it that way, but the ester is a protected version of a carboxylic acid. Okay, what else? All right, let's have you guys think backwards with a synthesis problem. Sorry. Excuse me. All right. Here are two synthesis problems. This one looks kind of scary, so go ahead and delay that one for the future. Start with this one. And I want you to make this using the method that we just talked about, starting with one of these two starting materials, the beta keto ester or the beta diester, and any other reagents you might need. Everybody gets the reference? I actually did this once, and the Claire Pepper was like, "You got to stop that. It's stressing me out." Okay. Got some notes here about significant figures. Aren't you glad you're not in that class? All right, take your time, but when you feel like you've got something, go ahead and tell your neighbor about it and compare notes and see if you can detect any oversights. All right, try to take another minute or two, finish up, and we'll talk about it all together. All right. Anybody want to use the Apple Pencil of Doom to draw it? Okay, come on down. See what you got.
Okay, so I synthesized it. Whoa, it's the laser pointer.
Oh, so just go up to the top of the screen and tap the pencil. There you go.
So I synthesized it from this. And I started off by reacting LDA with BR, which got me and then I reacted with LDA again, got me and then hydro. And then heat got me CO2, and then
Hey, thank you. Let's see, any questions, comments, concerns? Go ahead.
Does LDA cause a problem? Like it could be too strong, it would just remove the PR right there.
I think you could use LDA, the proton that's alpha to both carbonyls is pretty acidic. You wouldn't need to, so you can go with a much cheaper base, but there's nothing wrong with that proposal. Let's see. The stepwise, in terms of synthesis, you've shown all the intermediates really nicely. You don't have to actually do, if you were plotting this out, you could have just had this go straight to that. It's not like you have to intervene anymore. Once you add the acid and the heat, you're going to get this as a product, though you are right. First you form the beta keto acid, then the enol, then you tautomerize. Good. Okay. Very nice. Okay. So let's go ahead and take a break until like 5 after the hour or something like that. And then we'll come back, we'll do this, show you some biological decarboxylation, and then one more thing.